Hi all, I hope you had a wonderful spring break. Got a chance to relax, got a chance to think about something other than school for a little bit. We are going to finish up chapter 5 this week with 2 days of work in 5.5, and you'll have your chapter 5 test on next week. And the calendar is a little bit up in the air after that. So something to think about is spending some time on any missing assignments that you have remaining and getting in touch with me to set up the Zoom calls for that test early so we can address our pacing and figuring out what we're going to do for the remainder of the year. But let's finish up chapter 5 this week. And I look forward to meeting with all of you on Zoom. So the last integration technique that we're going to learn this chapter is using substitution. And what this is going to allow us to do is integrate with much more complicated functions. So, for example, if we're going to look here, we've got 2 times when we want to consider substitution. And of course, I've set them up so that they will look like these examples. So here we have the integral of 4x cubed times cosine x to the 4th plus 2 dx. So the first time we want to consider substitution is when it looks like the chain rule. Now, if you remember the chain rule from the derivatives, that was f prime of g times g prime. So when I say it looks like the chain rule, is that it is a product, which this one is, right? This is times, with composition. So what that means is that you have an inside function, and then the outside, and then what we would call the outside function, f, and then we have the derivative of the inside function. So this is already at the chain rule, which this fits. If we look here, the inside function, would be x to the 4th plus 2. Cosine would then be the outside function, and here is the derivative of that inside function. So we can say f prime is equal to cosine, g is equal to then x to the 4th plus 2, g prime is 4x to the 3rd. And you can back solve completely from there, but as it says in the title, substitution is a way to not have to do so much back solving and then figuring out what f is and doing the reverse engineering. What we will say here is just take your inside function and set it equal to u. And this is called u substitution. It's one of those cases we all just use u. I don't know why, but it's fine. Just take the inside function, set it equal to u. So x to the 4th plus 2. And then what you want to do from there is take the derivative. So du dx then is equal to 4x to the 3rd plus 0, which we drop. Now the reason that we use this method is that if you look here at this integral that we were given, we had cosine of x to the 4th plus 2, and then we have 4x cubed dx. So when we set u as the inside function, this becomes cosine of u. And here, we can also use substitution if we just solve for that statement here. So then I see that du is equal to 4x cubed dx. So I could substitute that right down here. And now, because these have matching variables, we can integrate. So cosine of u, the integral of cosine is sine of u plus c. And then we plug u back in, and we end up with sine of x to the 4th plus 2 plus c. And that's our integral. Now, the reason we use u substitution like this is sometimes it doesn't work out as perfectly as number 1 did, because you're not always going to end up with exactly that derivative on the outside. So let's look at an example where it's good to use our substitution, but it doesn't work out quite as perfectly. So another time you want to consider substitution is when you have a coefficient on the inside function. So remember, your inside function is always what you want to set equal to u to see if substitution is going to work out well. So we've got a coefficient on our variable. Makes us think, okay, want to do substitution. So we set u is equal to 2t minus 1. Then du dt is just equal to 2. Now, what you'll notice here in this integral is that I don't have any other terms out here. I don't have a 2, but I do have a dt. So what this just tells me is solve for dt. So in this case, I'll multiply both sides by dt. So du is equal to 2 dt. Divide by 2. And 1/2 du is equal to dt. So when I do my substitution, this is the integral of e to the u times 1/2 du. And the nice thing here is that this is a coefficient, so we can just bring that out and say, oh, well, that's 1/2 of the integral of e to the u du, which is 1/2 times e to the u plus c. Substitute our u function back in, 1/2 e to the 2t minus 1 plus c. And there's our final answer. You can also use u substitution for problems that look a little bit strange. And you're not going to run into too many of these, but I do want to show you this strategy also because, as you can imagine, knowing the integral of tangent is a really helpful one to just have off the top of your head. So here we have bound and tangent. So this at first probably doesn't look like a substitution problem. We only have one function. But if you want to be able to find the integral of tangent, the way that you set this up is you say, well, tangent is sine over cosine. And then we consider that in terms of a product as 1 over cosine theta times sine theta d theta. And here we can see that if I set u as equal to cosine of theta, then du d theta is negative sine theta. We have positive sine theta d theta, so multiply by d theta on both sides and divide away the negative, and we end up with a lovely coefficient when we substitute in, and that gives us the integral of 1 over u times negative 1 du, which is negative 1 times ln of u plus c. So the integral of tangent is negative 1, or just negative ln of the absolute value of u, which is cosine, plus c. So this is just a very helpful integral to know. Now, if you have bounds, which we do here, we can plug them in using the fundamental theorem of calculus, but there's also a nice trick that you can do to make this go a little bit faster, is when you have your bounds pi over 6, pi over 3, tangent of theta, d theta. When you do your u substitution, if you can do those with the bounds, just plug them into u. So cosine of pi over 6, because cosine is our u function, and cosine of, not pi over 6, the upper bound, pi over 3, I apologize. And this should be pi over 3, so that they match what's happening there. You can then plug those in, and you don't have to worry about any of those change in bounds. So this becomes the integral of negative 1 over u du from root 3 over 2 to 1 over 2, which is equal to negative ln of 1/2 minus negative ln of root 3 over 2. And we can use our log rules to say, all right, well, this goes into a denominator, this becomes positive. So this simplifies to the natural log of root 3 over 2 over 1 over 2, which simplifies to the natural log of root 3. If you have questions about substitution, I would love to hear them. Nominate any problems that you have from these problem sets in the forums, or if you're confused, please set up a Zoom call, and I can't wait to talk to you. Have a great day.